So what I want to talk about is a kind of certain view on dynamics of group automorphisms. So I must apologize in advance that this is not G mod gamma world, unless you accept R to the D as a G and Z to the D as a gamma, but which is stretching things. And I want to try and explain a kind of point of view and a few results and a huge sea of ignorance that I possess. So the setting is this. You think about all group automorphisms simultaneously. So G is a compact metric abelian group. T is a continuous automorphism. So examples to think of are toral automorphisms, but there are many others. And the question is, as you move around in this space of pairs, what dynamical properties exhibit rigidity and change in steps, and what dynamical properties change smoothly? We'll call those rigid or granular and flexible properties. And just to remind everyone, if you fix a compact group, then the quotient of the automorphism group by the inner automorphisms has a natural topology and is totally disconnected. This is very classical. As far as I know, it's due to Iwasawa in the 1940s. This, incidentally, is a fantastically cool paper that everyone should read, partly because of a footnote on the first page where he says that because of the conditions during wartime, he had to reconstruct proofs from the Math Review abstract of a complete subject. So topological groups studied by Iwasawa, he kind of did it by himself. I think this might be a screensaver, sorry about that. But anyway, so in this abelian setting, the automorphism group is always totally disconnected. That means that somehow it's kind of wrong to think about moving through the automorphism group as a way of moving. You should move through the parameter space of G's and T's simultaneously. Okay. And really what I want to do this afternoon is explain this diagram, or this table, which I once went to a talk in Maryland where someone put up an overhead of differential equations and said, I'm going to tell you everything I know this afternoon. I'm going to tell you everything I know here, and you should be reassured. There are many question marks. It won't take long. Don't know much. But on the left, I have dynamical properties. Entropy, of course, is familiar. Growth rate of periodic points in two versions, cheating and honest. I'll try and explain what that means. Merton's constant is just a parameter, a kind of analytic parameter that you can attach to a dynamical system of the right sort. The zeta function and its behavior is something we've been studying most recently. And here I have zero-dimensional or totally disconnected compact groups. And here I have connected compact groups. And these behave completely differently. So this is kind of a familiar thing in this kind of algebraic dynamics, that zero-dimensional groups are connected with positive characteristic phenomena and one set of issues. Connected groups are connected to number fields in zero characteristic and a different set of issues and a different set of things. And I just want to explain all these things, the different phenomena. There is one flexible thing here, growth rate. There is one flexible thing here to do with this Merton's constant. Everything else probably is rigid in the sense that you cannot perturb it. But almost none of that is provable. Okay. So the first one is entropy, and this should be familiar to everyone. So I will just go through it kind of quickly. Oops, not that quickly. So for group automorphisms, they are, by entropy, you could mean almost anything, topological entropy or entropy with respect to Haar measure or anything. The dynamics is completely homogeneous. It's the same everywhere. You can't tell where you are in a compact group by what happens to you under an automorphism. That means that the entropy can be computed via linearization or localization. You can compute it in a neighborhood of the identity, or you can compute it by lifting to some covering space. So the thing to think of in your head is a toral automorphism. You could compute the entropy by lifting it to a linear map of R to the D, where you could, if you were lucky, diagonalize or do all sorts of linear algebra things. But this is really, this statement is a linearization. So this is a metric open ball around 0. I intersect pre-images. I get something smaller and smaller. There's a characteristic decay in volume. M is Haar measure. And I measure the decay rate. And this tells me the entropy, which a priori is a global invariant about the whole system. But these are completely homogeneous systems. So what does this expression look like? So just to remind, this is, I simply take a metric ball, take the pre-image. Because it's a metric ball around a fixed point, I just intersect. I don't need to translate or do anything. I intersect, and it gets smaller and smaller. What I expect is the following. If I had a toral automorphism with some small eigenvalues and some large eigenvalues, then the phenomena would be that it's the inverse map. For automorphisms, it doesn't matter, but the inverse map, the large eigenvalues would be contracting. So I expect this intersection to have a volume that's something like epsilon to the d is irrelevant, the product over the large eigenvalues to the number of times I iterate it. So I expect this precise exponential rate of decay. You need to be a tiny bit cautious. Even on the torus, it's not completely obvious how a metric open ball's pre-image, which is a long thin set, might intersect again. And you need to check a little bit, but it doesn't, nothing bad happens. This means that the exponential decay in volume of this expression is precisely given by the sum of the large eigenvalues, or equivalently the sum of log plus over all the eigenvalues of the size of the eigenvalue. And I can write this as an integral of the characteristic polynomial, log of the absolute value of the characteristic polynomial over the unit circle. This is a kind of L0 norm of the characteristic polynomial. So this expression matters because, so first of all, this equality of this with this is just Jensen's formula in complex analysis. If I factorize f, I see it's Jensen's formula. And it matters because the thing on the right is a thing that other people studied somehow. Okay, this is the Mahler measure of the polynomial f, and it gives some insight into what sort of numbers should arise here. So remember, what I'm after is answering the question, can I change some of these dynamical properties smoothly? So if I compute the entropy of a group automorphism, could you find another one with a very nearby value of the entropy? So, as I mentioned, that's a linearization, really, that argument, or a localization. You can do it in greater generality. You can just do some algebra, but the hard case is the toral case, really. And you deduce that the set of entropies that arise is precisely the closure of the set of Mahler measures of integer polynomials. They'll be positive if you restrict to ergodic automorphisms, which is reasonable to do. So this is an old formula due to Sergei Yasvinsky. He phrased it differently, but this is somehow something you deduce. And then a classical thing from the 1930s, very nice problem, is the following question. So M of f is this integral. If I restrict to polynomials for which it is positive, that is to say, the only way this could be 0 is to be a product of cyclotomic polynomials. So I avoid those guys. I have positive values. Lemma asks if you can find small values of this expression. And roughly speaking, what happens is you want to write down an integer polynomial in such a way that it has perhaps some roots inside the unit circle, perhaps some roots on the unit circle, and some roots outside, in such a way that the product of the roots outside is as close as possible to 1. And what happens is if you make them small, then one of them escapes, roughly speaking. So if you cheat and permit one of them to escape, then you can make this expression arbitrarily small. but they kind of push back against you. And the smallest known thing is some 10th degree polynomial with a certain explicit number value, 1.1 something. And conjecturally, there is a gap. And of course, if there's a gap in these values, by this theorem of Jarzynski, there's a gap in the entropy values. In fact, you can sort of do all the bookkeeping and sort it out as follows. If Lerman's problem has the answer yes, then the possible entropies of compact group automorphisms is a countable set with a gap above 0. And if the answer is no, then, which no one expects, then there's a compact group automorphism with any entropy, which is wildly implausible. It would mean there's a toral automorphism with entropy log pi. No one believes this. The reason that closure arises here is because you can take sort of take infinite products, right? If the answer to this was no, right? That is to say, if there was no gap, then I could construct, it means I could construct toral automorphisms with entropy, any quantity, any small quantity you like, or smaller than any small quantity you like, and then take an infinite product of them. The entropy is the infinite sum, and I could get any value I want. So conjecturally, the answer to this question I started with is this is a rigid property. You cannot navigate amongst entropies in a way that lets you change smoothly from a small entropy, for example. That was connected, essentially toral. Zero-dimensional case is much easier. With your bare hands, you can prove that a zero-dimensional group automorphism has entropy log of an integer. They're essentially, they look like full shifts and they're glorified versions. So that's certainly rigid, and for connected, conjecturally rigid. Okay, periodic points. Oh, sorry. Was the next sort of dynamical property I wanted to mention. And there's a very nice example, which Alan Haynes has now improved very much. Don't know whether to call this an example or a theorem. I like this theorem very much. It's extremely ugly and unpleasant to prove. For any number, including pi, there is a compact group automorphism with exponential growth rate of periodic points that exists, meaning the limit exists, and is that value. Okay, so this is quite a strange statement. Means that if you have a compact group automorphism with a given growth rate, I can find other examples to perturb away smoothly, to just change these values. So this is, in this terminology, a flexible type of invariant. And unfortunately, the examples are non-ergodic. And that's really cheating. That's really very bad, because it's not, it just somehow isn't the right principle. These questions should be considered for ergodic group automorphisms, not degenerate ones. In fact, it's extremely non-ergodic. The way you construct these particular examples is to take an infinite product of finite groups, finite abelian groups, and you have automorphisms on each of them. The kind of thing you want to know in order to be able to do messing about like this is to know how long in an arithmetic progression do you have to wait before the first prime appears. Okay? So in fact, my proof of this uses a bound from Linux. You need some bound from someone, right? Doesn't matter what bound it is. Almost any bound will do, but it actually uses something really very difficult. And as far as I know, this is not an easy thing to prove. If you try with your bare hands, you need to think how to do it. And as I mentioned, Alan now has much nicer versions, where in particular you replace this question with a different question. If I measure a growth, if I ask for a different growth rate, right? If I ask for a polynomial growth rate or some sub-exponential growth rate, then you do the same construction, but you have to work much harder, of course. right? Low growth rates are difficult. So he has much lower growth rates. I don't know the details. Polynomial or something.
Yeah, the student.
Yeah. That's right. Christopher White and Alan Haynes. Yeah. So they have very nice, frankly weird results. I mean, you have to be me to care. But there these things are, but they're not ergodic, innately not ergodic. If I tried to impose ergodicity, then it's almost certainly completely not like this at all. The growth rates, when they exist, will be not often, and when they exist will be like powers of integers. You would expect this to be log of an integer if the limit exists on a zero-dimensional group, and most of the time you'd expect the limit not to exist. On a connected group, think torus, this is almost exactly Lemma's problem again. You almost certainly can't do this. This is on any solenoid. So the belief would be that if this limit exists, then you're looking more or less at a toral situation, and if it's a toral situation, then this quantity is a Mahler measure. That should be what's true. Okay, so we know something, but not much here. Nope. So, in general, and this is something that if you're not familiar with, I should explain. In general, the number of points of a given period is a wildly erratic function of n for a group automorphism. So let me try and explain why that's true. So the formulas you're used to are so what would I expect for a toral automorphism? You have some expression like this is the familiar thing, okay? Which is some product over eigenvalues of some quantity like this. And then you're interested in logarithmic growth rate. So I kind of know what to expect, and I know where to see difficulties. If one of these is inside the unit circle, it's asymptotically negligible. One of them is outside, it's asymptotically exponentially makes that contribution, which is one of these terms that contribute to the entropy. If, God forbid, it has modulus 1, but is not a unit root, then you need something, Baker or Gelfond or something, to tell you that this still converges, but it does. And so that's what you expect. But if I start messing with the group rather than the automorphism and wrote down a different group, a solenoid, a projective limit of toruses, then the kind of expressions I would expect would be things like some product over some valuations of a number field, some other product of the same sort of expressions, and some of these places might be infinite, and I might get an expression like this, and some of them might be finite. And then I get a completely different phenomena, like the simplest example being like this. So what does this mean? So maybe we not specify the primes. This is just the p-adic part of 2 to the m minus 1. So what this expression is I factorize 2 to the n minus 1 and I delete the p part of it. Okay. So I expect this to, every now and then, be much smaller than 2 to the n minus 1. And most of the time be as big as 2 to the n minus 1. But not much, much smaller. Unless I multiply by many of these terms. Potentially I have an infinite string of primes where I multiply, I delete those primes. So then how do I express, how large do you expect this to be? Well, you can't tell. So in particular, if I chose or rejected a prime randomly once, I do one infinite coin toss to select a set of primes, then I write down a system that looks like this. Then with probability 1, if there are infinitely many Mersenne primes, with probability 1 I have picked up infinitely many of them. Which means every now and then, but rarely, this whole thing is equal to 1. And equally, by the same argument, every now and then, but rarely, this thing is equal to 2 to the n minus 1. So the point is, as soon as you're away from torus, you have something that's innately erratic in the growth rate.
You mean you consider all the sequence for all the n's?
No, so what is happening here? A typical example would be you choose once a set of primes, P1, P2, and so on. That defines a system. Then I consider this expression for all n. This is the formula for the points of period n. So now I want to know the growth rate of this expression as n varies. And instead of the Diophantine problem I have here that's Bakerish, here I have an arithmetic problem that turns out to be just insurmountable or hard to understand. So because these expressions are so erratic, it's sort of a natural thing to smooth them more. Okay, so one of the standard things to do is to write down this quantity, and instead of a exponential growth rate of this number, I look for an asymptotic for this expression, where I sum over the closed orbits of length n. And in the domain where you have exponentially many points of period n, most of them come from closed orbits of length n. Right? This is the kind of territory one gets into. For a fast-growing number of periodic points, most of them come from long periods. But as you reduce the rate you're interested in, fewer and fewer of them come from long periods. And there's some critical limit where you have to think differently. But in this sort of domain, we're interested in exponential growth, and orbits and periods doesn't really make much difference. H is just a topological entropy of the automorphism. So now you could ask, what are the asymptotics of this expression as a measure of orbit growth? So this is the standard example, which I still find things I didn't understand about. Circle doubling map. So let me just run through it. Circle doubling map has 2 to the n minus 1 points of period n. So approximately 2 to the n over n points that live on closed orbits of length n. This is this phenomena that most points of period n came from orbits of length n. So it's just a calculation. That expression, that smoothed sum over closed orbits, is asymptotic to log n, because it's approximately the sum of 1 over n. And it turns out that as I move around in this space, changing the group and the automorphism, I will get asymptotics like this, multiples of log n. So this thing that I call the Mertens constant is this number. The main term in this asymptotic expression, what is it? And if you work hard, sometimes this is 2 or 3 terms and controlled errors and so on. So it turns out, after some effort, that this kappa is a flexible invariant in this domain. That is to say, I can construct group automorphisms for which kappa varies smoothly. This is joint work with Stefan Bayer and Salian J.D. and Sean Stevens at UEA. And having written this, I guess you can all see how to prove the theorems on the next slide. Okay, so here are these results we get. So first of all, for any value of kappa between 0 and 1, we can construct, without cheating, something ergodic, connected, a nice thing for which this asymptotic is kappa times log n. And this is how you do it. You construct a set of primes for which this expression behaves like that. And that's kind of all, that's the whole game. And then, because Stefan Bayer is a proper number theorist, he took us into different kinds of questions. It turns out you can do almost anything. You can make all sorts of asymptotics. For me, this was the interesting one, this first theorem. That was kind of striking, that there are completely different growth rates. Progressively more and more difficult, these constructions became very unpleasant. But there are different growth rates. There are genuine sort of continua of parameters in the asymptotics inside this space. And I should explain a little bit about how you do this. So it all boils down to statements about the rationals. So because we're trying to exhibit something, we don't need to think in general, we're just exhibiting examples. So the connected groups we study are one-dimensional solenoids, which are duals of subgroups of the rationals. And you can describe all of them. And if you try to repeat what we did, having chosen to start with q squared, it's a whole different thing. Q squared is fundamentally different to q. In particular, you can't write down the subgroups of q squared. So the subgroups of q are very nice objects. The easiest ones to understand are the subrings. You pick a set of primes. You consider multiplication by 2 on the subring of things that have denominators only from that set of primes chosen in advance. And you get a group endomorphism whose periodic points are counted by an expression like this. That's exactly this expression down here. And then the trick is to choose your set of primes so that this expression has the properties you were after. Oops. So actually statements about primes, and it's a little involved what one has to do. But to give you a flavor, this is a typical question where this is the kind of game you have to play. So you have some density that might not be rational. You want to pick a set of primes so that this has this asymptotic. This is not too bad, right? This is quite easy to do. But you're constructing a set of primes L, and you have other things you want to keep in mind as you go along. And you want to do this, get this density asymptotic in such a way that inside L I can find other subsets of primes that make this Euler product as large as I like, in fact be anything, in such a way that on the subset I choose I have convergence of this. Is a typical step. And it's horrible. This is not fun at all. And along the way you need to use knowledge about sets of primes. And I'm sure if anyone were inclined to, they could read this and improve how we do this and make it more sensible. But it seems innately there's a horrible construction somewhere inside here. So the last row on that table of properties was some statement like analytical properties of the dynamical zeta function. And that's something I want to try and explain now. So the zeta function is just a generating function for counting fixed points, points of period n. It's a formal power series. And it has a more natural or different associated thing, which is just the normal generating function. Then, so somehow in familiar examples like Tor automorphisms, these things will be rational or well behaved in some ways. So circle doubling map, 2 to the n minus 1 points of period n, zeta function is 1 minus z over 1 minus 2z. Other phenomena exist, okay? This is well understood. So this is a nice example, which it's not that hard to see, but it takes a little doing. There is a smooth map, there is some map, and hence there is a smooth map, with 2 to the n choose n points of period n. So this is just true. How would you prove it? Well, you first show there is some map. Okay, that is to say there is a bijection of the natural numbers with 2 to the n choose n points of period n. That's a combinatorial fact. The way you prove it is to prove that you can construct a so a map a map on a countable set. A bijection on a countable set I can think of like this. It's just a list of numbers of orbits of a certain length. So this has one fixed point, one orbit of length 2. Let's say this had 2 orbits of length 3 and so on. It's a list of numbers. And it's clear for any list of numbers here, there is a map, right, on a countable set. So let's call that sequence ON. Okay, so ON is completely arbitrary. But ON is not Fn, right? Fn is the number of points of period 2 in this map would be 3, right? It's these 3 guys. And in general, it's the sum over the divisors of n of d times OD. Because each orbit of length d has d points on it that will contribute to blah, blah, blah. So the statement, the claim that 2 to the n choose n is a possible sequence Fn for some map is the statement that this thing try and write it down. So the inverse of this relationship is this relationship. That is to say, if these are the fixed points for some map, then the number of orbits of length n should be this expression. But the number of orbits of length n should be 0 mod n because they come in n-tuples and should be non-negative because it's counting something. So this slightly strange statement that there is a map with 2 to the n choose n points of period n is the statement that this expression is 0 mod n and it's non-negative. Okay? This expression down here, which is a sort of absurd thing that's either true or false. It turns out to be true. Okay? Turns out to be true. You can just check it. The reason I mention that is then now if I know that I have a bijection of the natural numbers with a certain number of orbits of each length, then there's a very nice argument by Alistair Windsor that says there's a smooth map of the torus with the same number of orbits of each length. You can accumulate orbits without you can build orbits of specified numbers without getting any additional orbits as you go to limits anyway. You have to do some checking. Consequence of all that is that, for example, there is a map, or a smooth map if you like smooth maps, whose generating function, or whose zeta function, is kind of algebraic but not rational. And once there's one, there's many. Okay, so there are many maps for which the zeta function is neither rational nor anything very weird. Okay, and remember, I want to try and understand the phenomena of moving through this parameter space, what can happen. So, So in my parameter space of group automorphisms, I know something about this sequence of possible numbers that are the fixed points of a group automorphism. It has to be a divisibility sequence, right? Because the points of period 6, the points of period 3 are a subgroup of the points of period 6, and so on. Because it's a divisibility sequence, if I knew in addition that it was a linear recurrent sequence, for example, if I knew the zeta function was rational, then I know exactly what it is in principle. Okay, there is a completely unreadable paper by van der Poorten and Bezevin, I think, that says in the abstract, we classify the linear recurrent sequences that are divisibility sequences. But that's the only part of the paper I understand. The statements inside, I don't know what they mean. But in principle, we know exactly what they are when they're rational. But it also means other things. And this is very, very puzzling. So the statement I'm making here is, if I just write down any group automorphism and calculate its periodic points, I get a certain kind of integer sequence. It will be a divisibility sequence, and it has other mystical properties that I don't understand. And the reason I don't understand it is this example. So this is a fantastically simple example. Take a set with 6 elements and consider the permutation that fixes one of them. I know I have to do that because group automorphisms fix the identity. So I could have added another property. This sequence will never be 0. It fixes one of them and cycles through the other 5. Okay. This is a perfectly reasonable map, modest map. Its zeta function is this highly degenerate object. It is a divisibility sequence because you just check it is. It's certainly a linear recurrent sequence because it comes from a permutation of a finite set. But there is no group automorphism whose zeta function is this. There can't be, right? Because how could this be a group automorphism of anything, right? You can't have, this would be a group of order 6, 5 of whose elements all have the same order. Right? That's just not possible. So whatever mystical other properties, they exclude this. And so they exclude a whole bunch of things. There's some description. So we know a tiny bit about this. In fact, such a sequence has the property that its p part for any prime is also such a sequence, because you can kind of restrict to p parts of groups and so on. Okay, so as I mentioned, we normally have rational zeta functions. Or in familiar examples, we have rational zeta functions. As I've mentioned, the type of expressions you get in general have primes deleted from them. They're different shaped integer expressions. And what I want to show you quickly is a proof that for this example, for this explicit example, you get, not only is it not rational, it has a natural boundary. And the conjectural rigidity phenomena here is that for group automorphisms, if you're not rational, you have a natural boundary. You can't have the sort of algebraic non-rational examples can't be group automorphisms. Conjecturally, you can't quite prove this. So I now want to do an actual calculation. So just fix this in your head. I am studying the sequence 2 to the n minus 1 with the prime 3 deleted from it, as often as it appears. Okay. So, and remember, zeta was the zeta function x of the sum of fn over n, z to the n. Capital F is just the generating function. So if the zeta function is rational, then f, its logarithmic derivative, is rational. If the zeta function has analytic continuation, meromorphic extension, then f also does. So if I find a natural boundary for capital F, I find one for the zeta function. Then this is just a calculation, sort of calculation. So the expression I'm interested in is this times 2 to the n minus 1. So if I write down this auxiliary function, then r of 2z minus r of z is f of z. Just factorize the 2 to the n minus 1. So I can study r instead of f, and I claim that this, which has radius of convergence 1 now, has a natural boundary at 1. And therefore, by this relation, f has a natural boundary at a half, and therefore the zeta function has a natural boundary at a half. So now one must calculate what this is. So this, just to orient those of you not so familiar with it, the three part of 2 to the n minus 1 is less than or equal to 1. I mean, this is the reciprocal of the 3 part of 2 to the n minus 1. So it's less than or equal to 1. It's greater than or equal to the reciprocal of a polynomial. Okay? So this is a polynomially bounded above and below thing. Radius of convergence is 1. And there's a simple formula. This is, which I'll probably need 2 attempts to write down. This is 1 if n is odd. Sound plausible? Yep. And it's a third the three-adic size of n if n is even. Up to small errors. I think this is correct. Okay. So this 1/3 p-adic size of n is what appears here. When n is even, and when n is odd, I just have 1 as the coefficient. So I can write this function r as, well, this is running through the evens, so this is actually a function of z squared. Call it g of z squared. This thing is something else I don't care about. Let's call it h2, where g is this function. This thing is rational, right? Sum over the odd ends of z to the n is rational, so I don't care about it. So now I want to show that this thing g has natural boundary at the unit circle. And you do the obvious thing. If I have to sum over n an expression involving a three-adic part of n, I write n as a power of 3 times something coprime to 3 and sum over the power of 3. So that's all that's happening here. I sum over e and then over k. For k not divisible by 3, I do some calculations, some expression, some stuff. And after fiddling around a bit, I get a relation like this, where h is holomorphic, or is holomorphic where I care about it. So then I do a little separate calculation and check that g of 1 is a singular point for g. Okay, that you can do with your bare hands. And then this relation tells me that the cube roots of 1 are singular points for g, which I can then put back in and deduce that the 9th roots of 1 are singular points for g, and so on. So this functional equation tells me that g has a pole at any 3 to the kth root of unity, and therefore it has a natural boundary, has a dense set of singular points. So the proof is very unsatisfactory. I mean, this is a lovely argument, but it's completely ungeneralizable. If you tried to do it with 2 primes, you would fail. So you just add an additional factor, 2 to the n minus 1 5-adic, you would fail. And you need other methods. So all of this is building up to what we believe to be true, which is that we have this dichotomy that a zeta function of a group automorphism is rational or has this completely wild natural boundary behavior. So this is a dichotomy. So there's a classical, very beautiful theorem, Polio and Carlson, which says that a power series with integer coefficients and radius of convergence 1 has this exact dichotomy. It's either rational or has a natural boundary. So it's the same flavor of result. The difference is they can prove that. And this is our question, whether the same thing is true for group automorphisms. And it is tempting to think this is useful. It's not, because in our setting, I mean, you often have integer coefficients if you pass to the generating function. The zeta function itself doesn't. Radius of convergence is not going to be 1 unless you have some miracle like just happened in that functional equation argument, and usually is not going to be known, right? If I describe for you via some arithmetic condition an infinite set of primes, you won't know the radius of convergence of the function for this. You have no hope of knowing that. Just completely inconceivable. So there are other tools in this territory. One is Hadamard's. There are several theorems of Hadamard type that are useful here. I won't go through this. This is a completely amazing theorem. Okay, one of many Hadamard theorems. Completely amazing. I don't think he proved any of them. So this theorem says, roughly speaking, if I have a linear recurrent sequence, Bn, and another linear recurrent sequence, Cn, and I notice that their quotient is, for example, integral. So if one divides the other. The only way that can happen is for the quotient to also be a linear recurrent sequence. So this is quite a remarkable thing. Fabry I won't go into. There are many results that tell you information about quotients and products in this weird sense. So this is a quotient term by term. It's not a quotient of the functions, it's a quotient term by term. And in this game, you're constantly multiplying term by term. So any expression like this, if I know something about the analytic behavior of generating function of this, of sum of 2 to the n minus 1 zn, and I know something about the sum of 2 to the n minus 1 p1 zn, I would like to multiply them term by term and deduce something. And you sometimes can and sometimes can't. It's a whole jungle. Oh, as I mentioned, the radius of convergence, typically of what we're studying, you'll have no hope of ever knowing. So, as usual, I stick to one-dimensional solenoids. I do some algebra. Really, I just describe things in a certain way. And the parameter that varies here is a set of primes S, again. And I want to just illustrate, so you can take R is 2, I just have some explicit expression like this, 2 to the n minus 1 times the product over a certain set of primes of 2 to the n minus 1 p-adic. I take out the p part over a certain set of primes. I want to study this power series with this coefficient. And I want to just show a kind of baby case of this idea. I want to prove that this expression is rational if and only if I have no primes that make R, think 2, look like a non-unit. Okay, so this would be saying, as soon as I have a prime that isn't 2 involved, I get an irrational function at least, which gives me some hope of exhibiting a natural boundary. So let's think of a finite set of primes for which I have some interesting primes, like 3. Okay? Because S is finite, then the values that this expression takes on will live in a finitely generated extension of Z. I can just arrange things so that A is big and B is small, and get away from having absolute values. Absolute values are a big pain here. If anyone's computed or worked with the zeta function of a toral automorphism, you'll be familiar with this fact. You have to deal with the fact that the expression is the absolute value, it's not the determinant of A to the n minus the identity, it's the absolute value of it, which immediately makes you start to question why it was rational, right? It's not completely obvious. But if I take a linear recurrent sequence and take its absolute values, why do I get something that whose generating function is rational. You need to think why that's true. So here you have to do some fiddling about. And then there's this argument. If the generating function guy I started with is rational, then this would be a linear recurrent sequence. So by Hadamard, the real function f, sorry, this f, which is back here, sorry. Go back here. If this thing was rational, then this would have to be a linear recurrent sequence, which means that the function using these coefficients would also be, because I'm allowed to divide away, because these things live in a finitely generated extension. But then I can look at expressions like this. If this set of primes is non-empty, and has primes where this is equal to 1, then you could easily check that this expression takes on infinitely many different values, each infinitely often, which is something, just by Frobenius type arguments, which is something that a linear recurrent sequence can't do. So I deduced that this thing was irrational just because this set was non-empty, which was the statement I was sort of after. And that's a flavor of how you kind of start getting into using these powerful tools to end up in a position to apply Polya-Carlson or to do some other ad hoc argument. So if S is cofinite, if I have all but finitely many primes, then Polya-Carlson applies directly, because this polynomial bound tells you the radius of convergence is really 1. And in the end, we can show this dichotomy, that the zeta functions are rational or natural boundary in several cases. If the set of primes is finite and the dimension of the compact group is 1, it's cofinite. If the dimension is 1 and S has a thin complement, this is, so what? Right? I mean, you should think the parameter space here is all subsets of the primes. So being able to do it for finite and cofinite is not scratching the surface, really. If I tried to do this on higher dimensional groups, life is much harder. And for any experts, you will immediately understand how the next theorem is proved, or why the next theorem has the hypotheses that it has. You can, these expressions that look like this, some places, some number fields, some products of expressions like this, various valuations, that's all you have to deal with. So this is a very nice result of Richard Miles, that take any group automorphism, compute its periodic points, you have a formula like this, for what it's worth. I mean, it's not clear what it tells you, but it tells you something. Then we can prove the following version. If the topological dimension of the group is less than or equal to 3, and it's connected, and the set of relevant primes, so here it would be places of a number field arising, is finite, then the Polya-Carlson dichotomy holds in that setting. And the reason experts will immediately understand what's going on here is that we use the fact that there are no Salem numbers involved. So this is a mixture of arithmetic and growth. And for the growth, you do not want one of these guys to have modulus 1. You want to avoid Salem numbers. In dimension less than or equal to 3, the degree of the relevant number fields is less than or equal to 3. You have no Salem numbers. You kind of get away from some problems. And that's as far as we can go in proving this, or improving special cases of this idea that how the zeta function looks changes sharply, that it's rigid. There's these rational examples, necessarily countably many of them. There are only countably many rational zeta functions. Takes a little thought as to why that's true, but there are only countably many rational zeta functions, because to be a rational zeta function, your poles arise at reciprocals of algebraic integers. This is a beautiful argument of Bone and Lanford from 50 years ago. And then there's nothing, and then there's natural boundary. And it's this gap that is this kind of rigidity we were trying to understand. Okay. Thank you.
So, questions?
You said something about function field case?
Yeah, we just haven't done it. It must be easier, right? For all this stuff, function field case should be easier. The zero-dimensional ones. I think it should be easier. The connected case was the one to start to see, I think. But I'm not sure. I don't know.
Do you know any stuff for non-compact? I mean, have you thought about that at all?
They're not interesting. I mean, I should qualify that. I should qualify that. In Gmod gamma world, non-compact is extraordinarily interesting. But if G is abelian, then non-compact suddenly is not interesting. It doesn't have interesting automorphisms, roughly speaking. I mean, there are serious results, but it's not. I mean, it's not informative in the same way. I don't think. But there are proper experts in the room. But somehow abelian non-compact
So
automorphisms, I don't even know if they can be ergodic or something. There are some results, right?
No, I got it.
There are no ergodic ones. So they only become interesting when you're quotient. And the point is, I mean, the same is true for G, but the point is a non-abelian G has much more interesting quotients.
How about the input?
I think it's, so the same questions arise, but these are hard enough, is what I would say. I mean, I have no idea, to be honest.
Sometimes they have much less.
Yeah. But somehow this construction, these solenoids, it sort of makes sense, right? In wherever you see Z, you might well be seeing some subring of Q. So it all makes sense, but it's quite hard to navigate. So to me, the next thing would be understanding two-dimensional solenoids. That is the same as understanding subgroups of Q squared. That's a big mess. So plus, I don't know any technology that isn't abelian.
So I was wondering, is there any relation between the first two things that you consider? So there is entropy and there is growth rate of periodic orbits. Of course, in some cases it's closely related, in some cases it's different.
Yeah.
So is there any ways in how to relate?
I don't think so. I think there's just, I mean, in this setting, there's just this kind of universal inequality. That the lim sup growth rate of periodic points is less than or equal to the entropy. That's it. Probably, I mean, we have no idea what the possible lim sup growth rate of periodic points could be. And we don't know what the entropies could be. But there's always this inequality. Yeah, they're just different. And there are extreme examples where only the fixed point, only the identity is fixed point. And you lose everything.
If there are no other questions.
Thank you.